And we are going to talk deep and heavy mathematics. We're going to talk about manifolds because, as I ended our last lecture on, the requirement that locally we should always be able to go into a frame where everything behaves as it does in deep space, that is, in the special relativistic format. This means that locally, any geometry that we encounter in general relativity should be described by a space which is locally flat, and this is largely the biggest part of the definition of manifolds. So what we're going to do today is we're going to introduce, in a technical sense, what is a manifold. So we're going to start with a question. So what is a manifold? And despite the fact that this is going to get very deep and very technical, at the end of the day, there's actually a pretty intuitive sense for what it is, and then some very valuable but also somewhat intuitive products that come out, in the sense that we're just going to look at how things transform under our description of the manifolds. So let me start with an answer to this question, because if you're ever asked a question, the first thing you should do is give the damn answer. So here's the answer to this question. A CP n-dimensional manifold is a set M with a maximal atlas. Okay, so hopefully that was pretty straightforward in terms of its definition. So if there are any questions, no questions, okay, we'll just keep going. I'm going to draw straight lines as straight as I can and put a block around this definition. Okay, this is what I hate about online things, because normally if we were live, I would see you laugh or smirk or actually just get this horrific look on your face like, what's that thing? But this is what I actually want to do. So this is the definition, but clearly we've got a few things that we have to define in order for this definition to make sense. So for example, what does CP mean? What does maximal mean? And what does the word atlas mean? Okay, all of these are important things that we need to understand in order to make sense of this definition. And so we're going to take these one at a time, and we're going to start with the set M. And what we have in mind is that this is a set. This set is a collection of points in space, if we're talking about a spatial manifold, or in space-time, if we're talking about a space-time manifold, which obviously we're going to talk about in this class. So what I mean, of course, is just a set of things, a set of points, you know, so obviously these should be connected to each other because we can move continuously through space. So if I'm going to sit here and draw dots to illustrate the set, I'm never going to be done because I have to draw an infinite number of dots. So we're not really going to illustrate things in that manner, but that's largely what we mean when we say a set of points. And what I'm going to turn to now is the notion of what we call charts. So let's begin by breaking up M into charts. So break up M into what we'll call charts, and charts are going to get a technical definition as we go. So let's consider a space M, or a manifold M, which I can just draw with wiggly lines because maybe this isn't the boundary of the manifold. In fact, in this class, our manifolds will not have boundaries, but I'm just trying to illustrate what the space is. And then charts are basically small patches of that space which overlap in many instances. So maybe that's chart U1, this is chart U2, chart U3, and maybe there's a chart U4. I don't know, there's lots of charts. Okay. And one of the important things about these charts is that the collection of charts should cover all of M. Okay. So the space we're dealing with here is, of course, an n-dimensional manifold. And I don't know why my pen is doing that. It will do it from time to time. And that's the brief take on writing the word manifold, MNFLD. Okay. And now let me give a technical definition to what I mean by a chart. A chart are subsets of M that come with a 1-to-1 map, which I'll just generically call phi, where phi maps us from the chart to n-dimensional Euclidean space such that the image of phi is open in Rn. Okay? Now, if you look at that, you might be like, okay, I know what a subset is. It's just a piece of M. So, you know, a chart is a subset, but then you've got this technical terminology. You've got 1-to-1, and you've got open, and you know, what the hell do those things mean? So I'm just going to walk through these one at a time. So 1-to-1 means the map is technically what is called injective. And what we mean by this is, if this is my chart, U alpha, and I'm considering points in U alpha, and I'm mapping those points to Rn, then every point in U alpha should be mapped to a unique point in Rn. Okay? So this map would be the map of phi as it acts on A. It gives me back the point A prime in Rn, and this is what the same map phi does if I instead feed it the point B in U alpha. Okay? So I just want to remind you, a map takes a point in a domain and hands you back something in the range, but we're just going to consider this a map between two spaces. Points in U alpha get mapped to points in Rn. And one of the interesting things to realize is that this is not necessarily an on-to map, because we might not have a point in U alpha which gives us the point C prime. So as an aside, what we can say is that if we have a 1-to-1 map plus the fact that the map is on-to, this of course being injective, and the notion of on-to being what's called surjective, then we call the net thing bijective, which is the necessary criterion for what we call an invertible map. Okay, so what I have in mind is right now, if the point C prime is not generated by mapping from a point in U alpha to Rn, it's just a point that sits in Rn that doesn't come from the map, then creating an inverse is obviously difficult, because the inverse map should go from Rn. Oh, by the way, let me ask you all a question. Somebody answer it. Right now, I've got a dot over my PowerPoint from where my pen is hovering. Can you see that at all?
Yes.
Yeah, we can see that.
Okay, I just needed to make sure because on some Zoom meetings, when you're writing, people can't see the dot as it hovers.
I think that's just when you're annotating, not when you have a whiteboard.
Okay, that's good to know. Thank you very much.
Yeah, no problem.
Okay, so if the point C prime was not mapped from a point in U alpha, then where would the inverse take you? It wouldn't take you anywhere, okay? So in order to make this actually an invertible map, we need C prime to come from a point C, so that basically every point in the space, which is our image, comes from a point in the domain. And then we can just turn everything around and go backwards, okay? I'm gonna fix that to a C. All right, now I don't wanna get too hung up on this, but we can contrast one-to-one with the idea of many-to-one, which some of you are probably aware of. That's if you have the points A and B get mapped to the same point in the target space, which we might call A prime. That's a many-to-one map. And then a one-to-many map would be if we had a point in the initial space and it got mapped to 2 points. Okay. Many-to-one and one-to-many maps do not allow for inverses. Okay, so that's what one-to-one means here. And then we have the notion of open. Open can be defined in the following sense. Open in Rn, so this is in the special case of an Rn space or a Euclidean space, means the interior of an n-1 dimensional closed surface. Now, open can mean different things in different contexts, but since we're dealing with spaces, largely either Rn or Mn, that's Euclidean space or Minkowski space and in dimensions, we can consider an open interval or an open space in the following sense. So first of all, as an example, if we're in R1, then we can imagine the surface given by these two dots, which creates a closed surface in R1. Okay? So I'm just talking about these two dots, not the space in between or anything like that. So a surface in R1 is an R0. It's a zero-dimensional surface, and that we can represent by a dot. And now, if we take all of the space between the two dots, but we don't include the dots themselves, then we're dealing with a space which is open in R1. Okay? So this is just a useful definition of what we mean by the word open. Okay, it's a region where you can define it in terms of a closed boundary, and then you don't include the boundary in the definition of the space. You just take the interior or whatever the boundary wraps around. Okay? Any questions about this before I move on?
Yeah. Why does it matter if the chart is open?
You're going to see that in a few minutes. Okay? So I'll show you that. I'll show you why in just a few minutes. Well, I mean, actually, why does it matter that the chart is open? Well, okay, so if you take a closed chart, then you're not looking at a subspace which is isomorphic to. So let me argue it this way. This is R1. It goes to infinity and negative infinity. Okay. If you imagine a closed subspace of R1, So if you take a line and you include the two endpoints, then this is not isomorphic to R1 itself. However, if you take an open interval, then the open interval, even though it's a subsystem of R1, it is in some sense isomorphic to R1 because R1, you know, it goes to infinity, but it doesn't actually reach infinity because infinity is not a well-defined limit. Okay, so the R1 line does not actually include infinity and negative infinity, just like in this case with the open interval, it doesn't include the two ends that it's approaching. In the closed case or the bounded region, you actually include the edges. So if you're actually trying to do physics, the physics on an infinite line R1 is actually quite similar to the physics in the open interval of R1, which is very, very different than the bounded interval in R1. Does that make sense?
Okay. I think so, yes.
Okay. All right, so now the charts and the maps that are associated with them might sound kind of weird and somewhat abstract, but what they really just boil down to, so remember, the phi maps us from a region of the space into Rn. Really and truthfully, what this means is that we're assigning coordinates to the patch U alpha. So another way to imagine this is if we take a patch of the space, U alpha, the map phi, which carries us from U alpha to Rn, is really just equivalent to coordinatizing the space. Okay? So what I mean by that is phi takes a point in U alpha and sends it to X and Y, which are contained in R2. Okay, this is for a two-dimensional example. All right. As yet another example, we can imagine the surface of a two-sphere. Okay. Or a two blob or a brain-shaped two blob. I don't know what you'd call it, but you know, it's supposed to be a sphere. And we can imagine taking the surface of this and sending it to using theta and phi, which live on R2. So phi is mapping us from a point on the surface of the sphere to the coordinates theta and phi, which are elements of R2. So R2, in case you're not aware, if we coordinatize it with theta and phi, actually goes like this. All right. So does everybody see this? Even though theta and phi are sort of developed in terms of these internal angles for the sphere, the actual values of theta and phi are valued in R2. Okay. So now that we know what a chart is, so literally a chart is just, okay, I'm getting blown up with chat and I hope this is all serious. I'm gonna have a quick read over it. Quantum, I don't want to talk about quantum. Yeah, I'm going to ignore the chat room. This is going to drive me nuts if I try and entertain chat room questions. You can just ask questions out loud at any point that you have one. So now that we know what a chart is, we can define an atlas. So an atlas on the manifold M is a collection of charts. So we would say these are the sets which come with U alpha and phi alpha each. So we have a whole bunch of the U alphas. They completely cover the space. And that's going to be really hard to draw, by the way. So let me just go back to this. Yeah, so remember when I said that the chart should cover all of the space? That's actually hard to draw. I mean, I can just keep filling these in until I've covered everything, but that obviously makes for a nasty picture. But there you go, I did it anyway. Okay, so we have a collection of charts, U alpha. Each U alpha has its own map, phi alpha, and they're going to cover the entire space. And they, in order to form an atlas, there's going to be two conditions that have to be met by these. A, the union of all charts. U alpha is equal to M. Okay, so if I take the union of all of the charts, then I get back the original space which they were dividing up. And then the second condition, which is going to be a headway into some interesting stuff, is that the charts are sewn together with CP transition functions. Okay? Everybody on board? All right, I'm gonna look at the class for a minute. Are you guys on board or not? You should be nervous. I just wrote down CP transition functions, and you should be like, what the hell is a transition function, Flournoy? But nobody's asking me that question. Do you not need to know what a transition function is, or do you know?
What is it, Flournoy?
Oh, thank you. Thank you. I so appreciate it. I'll tell you what a transition function is. Okay, so what is the CP transition function? Okay, suppose that we have two charts which are overlapping. So we'll call this chart U1 and this chart U2. And one of the things that we know is that U1 comes equipped with a map, we might call it phi1, which maps us to an open region of Rn. Okay, so this is in an n-dimensional manifold. U2, of course, comes with its own map, which will map us to another copy of Rn. Okay? Now I want you to notice, coming back to this example here, the manifold that we're dealing with can be curved or whatever, but what you're mapping to is always flat space. Okay, this is one of the important aspects of this map. You might start out with a curved space, but the map from each chart carries you to flat space. And there's a very important reason why we want to have everything mapped to flat space, which we'll talk about in just a few minutes. Now, what I want to do is I want to consider a point P, which is in the overlap of charts U1 and U2. Okay? Now, if I apply the map U1 to P, that's going to carry me to a point in this copy of Rn, which we might call P1. That's the result of applying the map U1 to the point P. It will carry us, in fact, I can just draw it, it will carry us down to this point. So this is phi 1 of P. Similarly, if I take the same point and I apply the map phi 2, then that might take me to a point in this copy of the space I would call P2. Okay, so this is the application of map phi 2 to the point P. Okay, now with regards to that pair of points, P and P1, I can identify an inverse map. You can't do this to all the points, but because these 2 points and the map between them is bijective, I can define the inverse of the phi1 map to the point P1. And this just takes the point P1 and maps me back to the point P. And then I can do very similar to the point P2 and map it back to P. And that will be done by the inverse of map 2 on point P2. Now, is everybody following this path of lines that I'm drawing and the various maps that are being done?
Yes.
Yeah, but
Oh, well, go
I
ahead.
did have a question. So before we said that they were just one-to-one injective, and now are we just assuming that they're all bijective now?
No. So this is only the map between 2 points in this manifold. This is not in general. I'm just trying to show you an argument that I'm about to make. So no, you don't have to have the map phi1 be totally bijective, nor the map phi2.
All right.
Okay. All right, here we go. So now what I can argue is the following. P1, that's this point right here. P1 is just the map phi1 on the shared point P, right? But the shared point P, I can imagine, well, you don't have to imagine, I can write it, is the inverse of map 2 on the point P2. Okay, remember, I can take P2 and map it through the inverse of the phi2 map to the point P. So I can replace P here with this map. All right.
What does that open circle between phi1 and phi2 mean?
This is just composing the 2 maps. So it's another way of writing this. Without all the parentheses. So this is just saying take P2, do this map, and then follow it with this map. So that's just the symbology of composure of maps. Does that make sense?
Yes, thank you.
Okay. So now, here's the interesting observation. This is a map from Rn to Rn. Because this thing takes the point P2, which is an element of Rn, and it returns the point P1, which is again an element of Rn. So this is overall a map from Rn to Rn. Okay? Are we on board? So P1 and P2 both live on copies of Rn. Now this of course means that P1 would be labeled in Rn by its coordinates, x1, y1, if we want to use x and y coordinates to coordinatize the Euclidean space. Shoot, I don't know what is wrong with me today. And then point P2 would be coordinatized on its own space. Okay. And then the transition function or the transition map is what we would call phi1, 2, which is just the composure of phi1 with phi2 inverse. Okay? So if you think about it, this is what the map is going to do. It's going to give us the coordinates on Rn that is associated with chart U1, and it's going to provide functions which take the coordinates on the second one, and depending on the function, or sorry, that's 2, y2, dot, dot, x2, y2, dot, dot, dot. Okay? So the functions are just going to be determined by the actual maps that we use, and I'll do an example of this in just a minute so you'll get an idea of what the maps are. But what I'm doing, if you think about it, is I'm handing this thing the coordinates of the point in P2. That is, I'm handing it the values x2, y2, and z2. Okay, and then I have different functions which map me to the different components of the position in the space I'm mapping to. But at the end of the day, this thing is what kind of transformation? Is there any takers? If I'm going to start with, say it again.
Coordinate changes?
Exactly. This is just a coordinate change. This is all super fancy hullabaloo language to describe what we would normally just call a coordinate change. Okay? Now, I want to stress to you that the coordinates, in some sense, they're not natural on the curved surface. I mean, sometimes we have to define them in terms of these angles that we use to define the coordinates on the sphere. But here's one of the things that I want to iterate to you. On the sphere, we define, or we coordinatize the surface of the sphere in terms of these angles theta and phi, okay? And it's easy to think, oh, theta and phi, those are coordinates which live on the surface of the sphere, except the angles theta and phi are not well defined if the only surface I'm thinking of is the sphere. Theta and phi are defined by the embedding of the sphere into three-dimensional space, and then we draw these vectors that come from the origin to the point on the sphere that we're dealing with, and then we associate it with a theta and phi. So if you think about it, even though theta and phi for the sphere help us identify a point, they are not coordinates on the sphere. Rather, they are elements of R2, which is a flat space. Okay, so I'm hoping that you realize that these maps from pieces of a manifold into Rn, that's the principal way that we define coordinates. And now what I've just said is that in two overlapping patches, I should be able to do a coordinate change from whatever one map gives me to whatever another map gives me of the points which are on the overlap. Okay? Now, the reason why this is so useful is because now that we're dealing with maps from Rn to Rn, we can now talk about calculus, and in particular, derivatives. Okay? So you might or might not realize this, but most of the calculus that you've done has been the calculus on flat space. Even if you're dealing with, you're talking about a sphere, you've embedded the sphere into flat space, and then you parameterize things in terms of coordinates defined on the flat space, et cetera, et cetera. So this mapping to a subset of flat space is crucial in the ability to apply calculus to what we're trying to deal with. Okay, so let me just continue to get the rest of these words defined, and then I'll work through an example. So if the pth derivative of the transition function from the alpha to the beta chart exists, and is continuous, then we call phi alpha beta CP. Okay? So as an example, if P equals infinity, i.e. if we're dealing with C infinity, then we call phi alpha beta by the term smooth. So let me give you an example of something that is and isn't smooth, just to make sure you understand. So for example, I might say, if I consider a function of x, and the function were just these two lines which were joined at a peak, okay, then this has the degree of differentiability of C0, since the first derivative is discontinuous.
Excuse me, Dr. Flournoy.
Yes.
Doesn't differentiability imply continuity?
Doesn't differentiability imply continuity? So it depends on the degree of differentiability. So this function which I just drew has a well-defined first derivative, but the first derivative is discontinuous. If I plotted the first derivative of this thing, then I would have something like this.
Wouldn't the derivative be not defined, though, at that point where it changes?
Why do you argue it's not defined?
Because the limit of that function on the right would not be defined, right? At specifically the intersection of those two lines. Or I should say the limit of the left-handed limit does not equal the right-handed limit.
The left-handed limit does not equal the right-handed limit. Well, isn't that illustrated by this discontinuity in the derivative?
Yeah, I'm just like, so does the derivative exist at that point, though?
Does the derivative exist at that point? Well, I think we are going to have to more carefully define this function in this region.
Okay.
Which I'm not going to do.
Thank you.
Yeah, you're welcome, although that was a shitty answer, so I'll have to think more about it.
Only just slightly shitty. You'll get me something better.
Okay. All right. But if we instead chose a nice smooth function, say a sine or a cosine, then this is on C infinity. Okay, because we know that we can take an infinite number of derivatives of this and they're all well-defined and connected and smooth. Okay? We do have one more condition we can state, and that is if the C infinity transition maps is also invertible, then it is a diffeomorphism. And the word diffeomorphism should echo in your head from the discussed symmetries associated with general relativity, but we'll talk more about that in due time. In general, the
Can I ask a question?
Yeah, go for it.
So if you say like have like a parabola, and you take the derivative of that a few times such that you get like 0, would that be considered smooth or not?
Yes,
Okay.
because you can take the derivative of 0. Look, if I take this, I mean, forget a parabola. If I just take an infinite line, you know, the first derivative of this is going to be an infinite line like that, and the second derivative is going to be 0. The third derivative is going to be 0. Well, 0 is a continuous function. So this is a C infinity.
Okay. I didn't know if 0 was like a weird special case, but thank you.
Yeah, no. Okay. All right, so most of the coordinate transformations that we're going to work with are diffeomorphisms, so they are actually invertible. But you know, you can define your charts and their transition functions in certain cases where they're not diffeomorphic, but in most cases in this class, we will be using diffeomorphisms. So last but not least, we have maximal. So a maximal atlas is what we would call an equivalence class. That is, and sorry, I got to figure out where I am and where I'm going to. Okay, so I'm going to get to my example in just a moment. So basically, what an equivalence class means is I have one manifold. So I have one manifold that can be covered by many different atlases. I mean, just think about it. If this is the manifold M, I could cover it with that atlas, or I could use this atlas. Okay, there are obviously a gazillion different ways to cover the manifold. Okay, and this is doing it in the sense that we're covering all of the manifold by a set of charts such that the union of all the charts gives me back the manifold. Okay, what we want to do is we want to say, if I'm going to define the manifold by the atlas, then it shouldn't matter which atlas I use. I'm defining the same manifold. Okay, so don't think that just because you're using two different atlases that you're referring to two different manifolds. The manifold is defined by either of these or the collection of all of them. And that's what we mean by the maximal atlas. That is, it is an equivalence class that says you can work with this or you can work with this. You're describing the same manifold in either case. Okay. Now here's an important observation about the fact that a manifold has to have a maximal atlas. If my manifold were given by this, and I used this atlas to cover it, then the continuity of the transition functions are only important in this region. Okay, so if I'm going to talk about the degree of differentiability of the manifold, you might think that I'm only applying that condition to this overlap region. However, remember the manifold can be identified with any covering. That means that I could consider the manifold in this simple case in terms of two totally overlapping charts. The union of those two charts also gives me the manifold, but now the overlap function is defined over the entire space. So the maximal set is actually what allows me to take the degree of differentiability of the transition function and apply it to the entire manifold. Does that make sense? So going back to our definition of a manifold, a CP n-dimensional manifold is a set M with a maximal atlas. Okay, that was our in brackets definition of a manifold. So are there any questions about any of the words that are contained in this definition? All right, so what I'm gonna do now is I'm just gonna put all this fancy hoity-toity, super technical talk into a very, very simple example. We're gonna prove that S1, i.e. a circle, is a manifold. Okay. Now, to prove that S1 is a manifold, we only need to construct one representative element from the maximal atlas. Okay. So if I can just cover it with one atlas of charts, then I've proved that it's a manifold, but we should extend the definition of it as a manifold to the maximal atlas. But I'm just going to prove one set of charts actually covers the space. So first of all, what is the dimensionality of S1? Anyone?
1D because it doesn't have an area.
Yeah. So S1 is a circle, but not the interior. It's just the surface of the circle. So this is a 1D space. We often view it embedded in at least 2 dimensions, if not 3. But we're just talking about the ring, okay, the circular direction with the points on the surface. Now, how many of you think, and I'm actually going to look at the class array of people, how many of you think we can cover this with a single chart? Give me a thumbs up. I see 1, 2, 3, 4, 5, 6. Does anyone think it will take more than one chart to do it? I mean, we can obviously do it with many charts if we want, but we want to try and construct the simplest atlas. So the question is can we cover the entire circle with a single chart? And I see most of you saying yes. Unfortunately, the answer is no. We require, to prove that a circle is a manifold, we require a minimum of 2 charts, and you'll understand why in the course of this. So we're going to take this circle and we're going to label points on it in 2 different ways, and you'll understand why we do 2 different labelings in just a moment. So we'll label the points, and I want to be strict in the difference between labeling points and coordinatizing the space, okay? So in method 1, what we're going to do is we're going to take the circle, so I'm going to call this method 1, and we're going to label the points by an angle theta that starts at 0 here and then increases to 2 pi here. Okay, so that's method 1. And then in method 2, what we're going to do is we're going to start here, and we're going to let the angle phi run from 0 to 2 pi down here, going this way. Okay? Now I want you to notice that both theta and phi are going to run on the interval from 0 to 2 pi, where we do not include 0, but we do include 2 pi. Okay? Obviously, if I tried to do this, I would be giving two different labels to the same point because 0 is identified with 2 pi. So in order to only give each point one label, we're going to remove 0 from the set and include 2 pi. That way, every point only gets one label. Okay? Now, it might seem like we have just coordinatized the circle, right? I mean, we've got a label for all the points. But remember, we need charts that map to open intervals in R1. This is a closed interval in R1. At least it includes one side. So in order to satisfy the formal definition of charts, we need for the charts that we're going to cover this thing with to map to open intervals. So this is, of course, what we can do. We can take the circle and we can map it with two charts which overlap with each other in the following sense. We'll call this U2 and we'll call this U1. Okay? Is it obvious to everybody that the union of U2 and U1 equals S1? That if we take all of the points on both of those charts together, we'll get all of S1. Does everybody see that? I take your silence as a yes, which is good to hear. So let's formalize what's going on. So with the maps, defined by theta and phi, we can say U1 with the map phi1. And to define this map, what I can say is that theta, this is the label I'm using here, theta is just going to give me the coordinate in R1. Or I can say the simpler way to specify this map is that theta equals x1. For region 2, which has its own map, or sorry, chart 2, which has its own map, we're going to use the point label phi to give us the coordinate in R1, which will, it's the second copy of R1, so we'll call its coordinate x2. And of course, we can write down that simple map as phi equals x2. Okay? Now, what I want to be wary of is that the U1 is only on this lower region of the circle. So if I want to specify that lower region, what I can say is that I'm taking the values of phi, which are ranging from pi over 2 minus some small amount epsilon to 3 pi over 2 plus epsilon. Okay. And then the range of phi is going to be pi over 2 minus epsilon to 3 pi over 2 plus epsilon as well. Okay, so everybody stare at this picture for a moment. Remember these coordinate or these label definitions, and then think about the subsequent ranges that I can write down for each of these, given that they have a small amount of overlap. Does this make sense? All right, here we go. First of all, the image of each of these maps is open in R1 as required for a charts map? Okay, it does not contain the endpoints. So this is what we could not achieve by trying to use these label points as coordinates, because to use the label points as coordinates, we automatically had to include at least 2 pi. If we left out 2 pi, if we just did 0 to 2 pi, what's wrong with trying that? I mean, that's an open interval, but what's wrong with it?
We're missing a point.
Yeah, you're not covering the entire space. Okay. Well, what if we did 0 to, 2 pi plus epsilon? What about that?
It's not 1-to-1 anymore.
Exactly. Okay. So we can't take a single covering of the circle and give ourselves this 1-to-1 map with an open image in R1. We need to use 2. All right. Okay, so now all we need to do is check and make sure that these form an atlas. So do these 2 coverings cover all of S1? The answer to that is yes. The next question is, are these transvection functions CP for some P? So we can consider the overlap between 2 regions. So we'll just take this example. So we'll take U2, U1, and this is going to be the pi over 2 plus epsilon, and the pi over 2 minus epsilon part of U2. So we're talking about this overlap right here. And then this is the 3 pi over 2 plus epsilon and the 3 pi over 2 minus epsilon part of U1. Okay. And so we can ask ourselves, what is the transition function if I want to go from the target space of the map from U2 into R1 to the target space of U1 into R1? And so we can ask, what is phi 1 composed with the inverse of phi 2 as it acts on the point x2? Well, that's just x1. And this map is going to be basically phi 2, 1, which is x1 as a function of x2, and the functional form of that is just x2 plus pi. Okay, can everybody see that? I mean, how do I get from this value to this value? I just add pi to it. Okay, now this is the map from the R1, which corresponds to the target of the map of the atlas of the transit, of the map from U1 into R1, and X2 is of course the image of the map from the manifold into the copy of R1 associated with the transition, or with the map from U2. How many times can you take the derivative of this and get a continuous result?
Infinite times?
Yeah, we can do it an infinite number of times. So this manifold is also called what?
Smooth?
Yeah, this is a smooth manifold, which you might have guessed. And my pen won't let me write the rest of this word. Okay, a circle is a smooth manifold. Okay, and we can do similar for the other overlap. And of course, we'll find the same result, that the transition function on both overlaps is an infinitely differentiable or smooth map. Okay. So does everyone sort of understand the steps in proving that the circle is a manifold? We have to first of all build a representative atlas of the maximal set. So you don't have to show that every single atlas is satisfies these conditions. You can just show that one of them does. And then what you have to do is you have to show that the map or the atlas is composed of a set of overlapping charts, which A, completely cover the manifold, and B, each chart comes with a one-to-one map that goes to an open image in the space on which you're defining the coordinates. And then just to determine the continuity or the smoothness of the space, we check the transition functions. And in this case, it comes out to be smooth. So are there any other questions associated with this? And I know this involves a lot of ideas which you may or may not be comfortable with. This is a degree of mathematical precision which we will abandon in due time, trust me. But I'm just trying to get you a sort of thorough introduction to the notion of manifolds, because manifolds, they are the key ingredient in all space times and general relativity. So, you know, the more rigorous your understanding of them, the sooner you will be able to sort of let go of that level of rigor, but appreciate some of the details that underlie it as you're working with manifolds as we move on. All right, I'm gonna stop with the share. We've hit our end mark, 6 past. I tell you, I can't wait to get back in front of your faces in person. I hate doing these things purely online. So I will see you all on Tuesday of next week. Yeah, so sorry, let me at least show you my face for a moment. Are there any questions before we dispense? No questions? All right, well, you were all able to load your quiz solutions into Canvas, yes? Anybody have any issues with that? Okay, I'll load you up some new homework questions to get working on for next Thursday. But otherwise, sayonara.
Thank you.
You're welcome.